Okay, let's take the third and final video in this lecture, which is to now talk about series fan-out, which is complementary to the parallel fan-out that we considered before. Now, admittedly, this is a little bit less common, but it could happen if you have, for example, the output of one logic gate, which is simultaneously connected to two other logic gates that are in series with each other. So let me try to draw this as a circuit. All right, here's a transmission line. It has transmission line impedance, and it's going to divide up into two transmission lines. I'm going to draw them like this. All right, this will be transmission line Z1. This will be transmission line Z2. And to connect everything in series, I'm going to go like this. I'm going to go bottom of Z0 to the bottom of Z2, top of Z0 to top of Z1. Then I'm going to connect the bottom of Z1 to the top of Z2. You can see here that Z1 and Z2 are basically in series with each other. In other words, if I pretend like I've got a little inductor, right, and capacitor that represents that first branch, then you can see that these inductors are now in series with each other. And so that's why this is called a series fan-out. All right. So let's again consider the case where we have a voltage coming in. We'll call this V in. And we're going to have a reflection coefficient right here. I'm going to call this gamma 0, 1, 2, which is the reflection coefficient for a wave coming along transmission line 0 and encountering Z1, Z2 on the junction, right? And so again, we're going to have something that hopefully should be pretty familiar. We're going to have something to represent the load minus the line Z0 divided by the sum of that. So what is in this load? When this voltage encounters a transmission line, it basically sees the sum total of two transmission lines because they are in series. And so instead of this question mark, I'm going to put in the series combination of Z1 and Z2, which just means we add them up. Z1 plus Z2. And so we've treated the load as if it were the series combination of Z1 and Z2. And you can repeat the same process over here. All right, this will be gamma 1, comma 0, 2, which will be equal to Z0 plus Z2 minus Z1 divided by Z0 plus Z2 plus Z1. And you can repeat the same process on this third one as well, and hopefully you get the idea. All right, so that's the reflection coefficients, but let's now consider the transmission, because the transmission gets a little more complicated. All right, in the case of the parallel fan-out, we said that because the transmission lines are connected in parallel, let me go back to that. Because these transmission lines are connected in parallel, we can guarantee that the same voltage appears across Z1 and Z2, or the same voltage is transmitted into those two transmission lines. For the series case, we can no longer say that. Instead, we can say that the current that's injected is the same in both of those transmission lines. Because think of this as if I've got a voltage that is feeding these two different transmission lines that are in series, Z1 and Z2. I can confidently say that the current between Z1 and Z2 will be the same, but clearly the voltage does not have to be. Okay? And so let's ask the question now, what is transmitted into Z1 and Z2? So first, let's figure out what the transmission coefficient is, the same way we did before. Tau equals gamma 0, 1, 2 plus 1. So that's the transmitted coefficient. This will be tau 0, 1, 2. All right, but what happened to that transmitted coefficient, that's transmitted voltage, is it's going to be divided up between Z1 and Z2. So we're going to have a voltage wave in here in which we're going to take our V in. We're going to multiply it by the transmission coefficient, 0, 1, 2, and we're going to have to multiply it by a resistor divider between Z1 and Z2. So this will be times Z1 divided by Z1 plus Z2. This will be the value of the voltage wave that's injected into transmission line 1. For transmission line 2, it will look very similar. V in, take the original voltage, add up the transmission coefficient, or multiply it times the transmission coefficient, and then apply the opposite end of the transmission line, Z2 divided by Z1 plus Z2. You'll notice that the sum of these, if we added them together, would be equal to Vn times tau 0, 1, 2. If we added those two up, so this is what we expect. This is just a transmitted wave. But because these two transmission lines are in series with each other, that wave is divided up proportionately between those two transmission lines. Okay, so this is called a series fan out. And again, this is a little bit less common, but still important for a number of applications. But you could still treat it the same way that we have before. You just have to be careful about the transmission and reflection coefficients. But once you've established this capability, everything else works exactly the same. Reflections on the load work the same as before. Reflection at the generator work the same way as before, but you may end up having multiple reflections to account for. And it's also important to note that whether a wave is coming from transmission line 2 or from 0 or for 1, you're going to get different transmission and reflection coefficients for the three of those. So as long as you keep track of all that, though, it's the same simple rules for series fan out. So in this video, we've now reviewed the way multiple transmission lines connect together. In the next lecture, we're going to consider the opposite effect, basically where we start to turn things off or disconnect a battery. And we'll have to consider how a circuit discharges or how it reacts to the negative side of a digital circuit.